Good morning. In this particular video, I'm going to discuss the shortcut distillation in Aspen Hysys, and after that, I'm going to discuss the rigorous distillation in Aspen Hysys. I'm going to open first the PowerPoint for the shortcut distillation. Okay, so this is the PowerPoint for the shortcut distillation. Okay, so as you can see, we're going to use this particular icon in the Aspen Hysys in order to perform the shortcut distillation. So the shortcut distillation will provide with an estimate of the number of stages or plates that you're going to use in the distillation. Okay, so the algorithm of the shortcut distillation in Aspen Hysys is based on the FUG method. So F stands for Penske equation. So if you still remember, using the Penske equation, you'll be able to calculate the minimum number of stages. So as you can see, it uses XDLK. LK stands for light key, or this is the more volatile component. Generally, this is also the XD, the usual XD. Kasi the light key is also the more volatile component, is the default XD that we use in distillation calculation. And then, syempre, XWLK is also the default XW or XV. Now, XWHK, this is the heavy key. HK stands for heavy key. This is the less volatile component. So if you have a binary distillation system, XWHK, if you still remember, is just 1 minus XWLK. Pero in the case that if you have several or greater than 2 components, this is not equal to 1 minus XWLK, or and then also we need the alpha LKHK. This is just simply alpha AB, or the relative volatility. So you can calculate using the Penske equation. You can calculate the N minimum. And then if you still remember the Underwood equation, you'll be able to calculate the minimum reflux ratio. Reflux ratio is the ratio of L with respect to the distillate, L over D. So remember, reflux is the amount of liquid that we return to the column, okay, divided by the total amount of product that we withdraw from the column. So this is the reflux ratio. So as you can see, the Underwood equation enables you to calculate the minimum reflux ratio. So the first equation enables you to calculate theta. So you need the quality of the feed value. So if you still remember, the quality of the feed value is this is the mass fraction or the mole fraction of liquid in the feed. So if you have a saturated liquid feed, Q is equals to 1. If you have a saturated vapor feed, Q is equals to 0. And then this alpha i's, the alpha i's right here are the relative volatility of each species. Okay, and then XFI, this is the composition, the mole fraction of each element, of each chemical element or chemical species in the feed, XFI. And then after calculating theta, we're going to use the theta on the second equation to determine R minimum. The only difference on the second equation is you're going to use XDI. So XDI is the composition of the distillate. So after finding N minimum and R minimum, we're going to use these two values on the Gilliland equation, the third equation. So the Gilliland equation, as you can see, will enable you to estimate n. N is the actual number of stages. So you need to have a value of the actual R, or the actual reflux ratio. Generally, this is 1.2 to 1.5 times that of R minimum. So pag hindi given sa problem, you just use 1.5. Multiply 1.5 times R mean, and then you're going to get your R. And then after that, you'll get the actual number of stages. So this is how the shortcut distillation is programmed in Aspen Hysys. Okay, so let's review the distillation system. So these are the plates that we try to estimate in the shortcut distillation. How many of these plates? This is N, capital N. So as you can see, we have a condenser over here. So basically, the condenser liquefies the vapor coming out of the column, and then it divides into two. The one that goes back to the column is known as reflux, and then this is your distillate product. The other stream is the distillate product. And then at the bottom of the column, you have a reboiler. It's a reboiler. So basically, what a reboiler does is that it vaporizes a portion of the liquid coming out of the column, and then return this at the column, inside the column. And then you have the other stream is your bottoms product. So those are the for review purposes, multi-stage distillation process. Okay, so this is going to be our problem. Stream containing ethylene and ethane must be separated. 68.5 weight percent ethylene and 31.5 weight percent ethane. And then ang feed natin, this is the composition of the feed, And then we will be assuming that this is saturated vapor. So later, vapor fraction would be equal to 1. And then 7,300,000 pounds per day is the flow rate of the feed. So we wanted a recovery rate of ethylene must be 99.9%, and the recovery rate of ethane must be 99%. So in the tutorial, it is specified that the concentration of the product, the distillate, is 99.98% ethylene, and then ethane at the bottom is 99.96%. So yun, we need to estimate the number of theoretical stages, and also we need to estimate of the refluxation. Basically, these two values, after getting this, you can input this to a rigorous distillation in Aspen Hysys, and then you'll get a much accurate simulation of the distillation process later, on the second part of this tutorial. Okay, so let's proceed to Aspen Hysys, and let's do this simulation. Okay, we're now on the Aspen Hysys window. So what I'm going to do is I'm going to open a new case. So let's generally start with that. Let's open a new case. Okay. So as you can see, the first part of Aspen Hysys simulation is to add components. So we're going to add ethane and ethylene. So generally you can find ethane right here. Just click ethane and then click add. Tapos type in ethylene. In order to find ethylene, you need to type in ethene. Ethene is the IUPAC name of ethylene. There is ethylene. So just add ethylene. Okay. And then we're going to use, let's proceed to the fluid package as a second part. That's the second step of the of Aspen Hysys. Click fluid packages and click add. And then we're going to use Peng Robinson. So just click Peng Robinson. Okay. So at this point, no, kita niyo yung green na yon. We're now ready to proceed to simulation. So in the simulation, just click on the columns since the shortcut distillation is under the columns. This is the shortcut distillation. If you're going to put the mouse pointer over these icons, the description of the column will be read. So if I put it over this particular icon, it says it's a shortcut distillation. So drag and drop this in the middle of the white screen, and then click on the white screen, and then double click on this T100. This is the shortcut column. Double click. And then the first step is to name all of this stream. So generally for condenser duty, we use Qcon. Then distillate, I'm going to use DIST. You can use any name you want. Wedding numbers. Then reboiler duty, I'm going to use QREB -Reb. And then for bottoms product, I'm going to name this bot. Okay. So feed, I'm going inlet, you're going to call this feed. Okay, so that's it. And then after naming all these streams, I'm going to click worksheet. So under worksheet, I'm going to enter the different state or properties of the feed. For example, the vapor fraction is 1 since it's a saturated vapor. So let's assume it's a saturated vapor, so 1.0. Okay. And then the tutorial, the pressure is 350 psig. You can check the tutorial. So try to change the unit to psig. Okay. Tapos mass flow. So if you still remember, the mass flow is 7,300,000. And that's pounds per day. Okay. So after those data are entered, you can now go to composition. So click composition and then enter 0.315 for ethane. This is in mass fraction. Okay, and then ethylene enters 0.685. And then transfer the composition basis to mass fraction. Okay, enter it again. 315 and 0.685. Okay, and then press OK. So we now have the composition. And then you can check if the feed stream has converged. So as you can see, pag nag-converge siya, may mga data na siya for temperatures, molar flow rate, etc. No? So we have successfully converged the feed. Feed stream. Ibig sabihin, kompleto na siya ng data. So the next step is go to design and then go to parameters. In this particular data blanks, you need to specify the light key. So in this particular case, ang purpose kasi nung shortcut distillation natin is to separate ethylene from ethane. That's obvious, Pero in some other process, for example, in your plant design, it's not that obvious, hindi siya binary, That's what I'm trying to say. So if you're using shortcut distillation and then the system is not binary, You have 3 or more components. The light key, you can determine the light key from the name of the column. Halimbawa, it's a demethanizer. So generally, the light key for that particular purpose is methane. Because that particular column, ang purpose niya is to remove the methane. So the light key would automatically be methane. And then you can randomly choose any key to any heavy key, to represent the to be the heavy key. That's the way it works, no? So in this particular case, our light key is ethylene. So just choose ethylene. And then syempre, the other one, ethane is the heavy key. And then as you can see, ethylene happens to be the light key because it contains less number of hydrogen. Thus, it has a lower molar mass, and thus it is more volatile. Ano? So that's why it's the light key. It's the more volatile component. And then in the tutorial, it is specified that the mole fraction of light key in the bottom is just 0.002, no? 0, 0, tatlong 0, and then 2. So you will have a 99.98 ganun, ano? Concentration in the bottoms. Okay, so just press enter. And then for heavy key, you can up 0.0004. Check ko lang ha sa tutorial. No, it's only 0.002. Mas fraction na nga pala. 2 zeros only. I'm going to change this one. Just 2 zeros. And then this is 0.004. Okay. And then the condenser pressure in the tutorial is 300 psig. It's given, no? I'll just change this one to psig. Also, the reboiler pressure is also 300 psi. Oops. Okay. Look for PSIG. Close. So, yun. As you can see, upon entering the condenser pressure and reboiler pressure, you now have the minimum reflux rate over here, 3.891. So, just kindly check on the tutorial, and this is the correct minimum reflux ratio on the tutorial. So in practice, if you have a minimum reflux ratio, just get your calculator and then multiply this by 1.5. So you will have the external reflux ratio. After entering a value for the minimum reflux ratio, you will have the number of stages. So in this particular tutorial, the prescribed value for external reflux ratio is 4.5. So I'm just going to enter 4.5. And then after entering that, as you can see, all the green bar over here, it means that the shortcut distillation has converged. It's able to calculate the number of minimum of stages, actual stages. So you can check it by clicking the performance. So here's our actual number of trays. It's around 76.388. Enough? So this is the actual number of trays. The minimum number of trays is 34.379. The same as the value in the tutorial. So I hope you can do and understand the shortcut distillation method. And then again, this is ang algorithm nito is based on the FUG, Pensky Underwood Gilliland equations. So kaya hindi syempre alam niyo naman yun, kaya hindi ginagamit yung McCabe-Tell kasi graphical, mahirap siyang i-convert sa sa code. Mas madali yung mga formula lang. Okay? So next, we're going to perform rigorous distillation. So basically, rigorous distillation, you're going to drag and drop another icon, no, the distillation icon, and then basically you have 5 pages to fill up, no, and then after filling up those 5 pages, you need to fill up the conditions for your feed, and then just run the simulation, and it should converge like this one. Of course, the rigorous distillation will show you a more actual or a better figure compared to the shortcut distillation. So as you can see sa shortcut distillation, wala siyang condenser, wala siyang reboiler. It's just a column and then you have the strings. So mamaya makikita niyo, ma-observe niyo, mas maganda yung rigorous distillation drawing. May condenser at saka may reboiler. And the simulation is much more accurate. Okay. So let's proceed. Let's do the rigorous distillation simulation tutorial. So we're going to get a new case. So file, new distillation. I'm just going to check na nasa distillation. I just make sure na nasa Aspen Hysys ako. Walang ulit yun ito. So this is, yeah, I've chosen file, new case. Okay. So I'm going to add components. Ethane at ethylene pa rin. The same composition, 31.5% ethane, 68.5%. The same pressures, 350 yung feed, 300 yung condenser. Tapos yung feed saturated vapor. Yung specs niya, dapat daw makaproduce tayo ng 5 million pounds per day ng distillate. Tapos dapat ang kanyang composition ay greater than 99.96. Yun yung dalawang specs. So, yung iba puro default na ng Aspen Hysys. Let's try to add components. Yung pa rin yung components, ethane pa rin at saka ethylene. Ito yung ethane, sa kabilang. Tapos yung ethylene, para makita nyo, ethane yung itinatay pa yung IUPAC name. Ito yung ethylene. Just add this. Fluid package natin, pa rin, Peng Robinson pa rin. So just add a fluid package, just press the add button. Tapos Peng Robinson. Okay, so pag lumabas yung green dito, it means ready na. So let's go to simulation. So sa simulation, click column. Columns, ito yung rigorous distillation. Distillation column subflow sheet. So just drag this on the white screen. Okay. Click on the white screen para mawala yung yung red. Tapos double click this. And then fill up the 5 stages. The 5 pages, sorry. Okay, so the first one is the condenser stream. So let's call this Q1. Just like a shortcut. We're going to use a total condenser. So pag sinabing total condenser, all of the vapor is liquefied. No, generally this is a default case sa condenser kasi relatively cheap lang naman ang cooling water. Tapos let's call the distillate as ethylene. This is our product. Ethylene is used for polymer production, for plastic production. This needs to be very pure kasi polymerization, pag hindi pure, nagkakaproblema. Okay. So in the tutorial, we're going to use 125 stages. So change this to 125. Okay. So after that, name the reboiler energy stream as QREV. And then the bottoms, we will going to call this as ethane kasi most of this is ethane, 99% plus. This is ethane. And then sa tutorial nyo nakalagay doon that we're going to name this stream as feed. Okay, so just type in feed, and then this one enters at 90th plate. So just click 90. Okay, so that's it. And then after entering this, you're going to see that you can now click next. So just click next for the second page. So on the second page, just use the default 1 screw regular Hysys reboiler and then click next. So this is just the default And then on the condenser pressure, don't change this, the pressure drop. Di naman to binago sa tutorial. So the condenser pressure, we're going to use 300 PSIG, kamukha sa shortcut. Kasi may pressure loss na ano. Pumapasok siya ng 350 PSIG. So may konting pressure loss. So ito 300 na lang. Okay? And also the reboiler pressure is also 300 PSIG. Okay, and then click next. What is this? Fourth page, fourth page, optional temperatures. Just leave this blank and then click next. So fourth page, blank lang, and then click next. And finally, we have the final, final page. So dun sa tutorial, may lalagay pa kayo dito sa liquid rate. Kaya lang, napansin ko, wala na yung pounds per day. So just leave this blank. The fifth page, just leave this blank and then click done. This is page 5 of 5. Just leave this blank and then just click done for the fifth page. So, ganun lang naman. Karamihan naman doon sa mga pages, kung ano rin lang yung default ni Aspen Hysys, hindi lang yung ginamit natin. So, what we're going to do next is to complete the data for the feed. Kailangan natin i-convert yung feed, tapos iraran lang. So, just go to worksheet, this one over here. So, go to worksheet and then enter the data. Saturated vapor tayo, Saturated vapor. So, ang ating vapor fraction ay 1.0. Okay? Tapos ang pressure natin ay 350 PSIG. You can check the tutorial, 350, 350, and then change the pressure, the units to PSIG. Okay? Tapos, the mass flow is 7.3. 7.3 million, 7.31 million. Okay? And then change this to pounds per day. Okay? So, and then go to composition. This is where you're going to enter that it is 31.5% ethane. By mass? Just 0.315. 0.315. Enter. Tapos 0.685. Okay, and then transfer this to mass fraction. Type it again, 0.315. Dapat tinransfer ko muna sa mass fraction. Bago ako nag-type. Hindi naman. 0.685. And then enter. Ayan, okay na, Okay. And then check if the feed has converged. So you can tell if the feed stream has converged pag meron siyang value ng temperature, etc. Nag-converge na siya, And then the next thing is you need to have two specification. So before you can run this, So just go to the parameters. Tapos design, and then under the design, you have the specs, So you can check the spec summary. We're not going to use the reflux ratio on the tutorial. What we're going to use is the distillate rate. So the distillate rate on the tutorial is specified to be 5 million pounds per day. So when you work on your own on the plant design, ang general na specs is the composition ng product nyo, So that's generally that's one, and also the reflux ratio. So yung reflux ratio, you can get it from the shortcut distillation. No, this one. This is the reflux ratio. And then the other one is the specification, is the composition of the distillate. So, yun. So just enter the distillate rate given in the tutorial. It's 5 million. Okay, just click the distillate rate. So you can change the unit to mass kasi mass yung given natin. And then you can now enter 5 million pounds per day. So just be careful. This is just 500,000. So another zero. 5 million. And then change this to pounds per day. Medyo magkaiba na yung yung tutorial kasi natin is 7.0. Ito 9.0 na yung ating software. So medyo magkaiba na ng konti. Pero basically ganun din lang. And just close this one. Napasok na natin yung product rate. So the next is you click specs. You click specs so you can add a specification. So generally dito nire-retrieve yung composition. So just go to column component fraction. So just click this one. Add the specs. You choose this one and then add the specs. So you replace this with the stream. Okay. Tapos I think this is correct, This is mole fraction. Tapos we're going to choose sa tutorial lang meron kasi is the ethane, no? So sabi yung ethane daw it should contain 9 times 10 to the minus 4 ethylene mole fraction. Okay, so just type in 9 E negative 4 and then enter. So that means ang kanyang ethane ay 99.91%. Okay, so those are the two specs. You need two specs. You need two specs. You need two. You always need two. So ang ginawa natin is the distillation rate. That's the first spec, and then the second spec is the composition of the bottoms. It should be 99.91%. Okay. So with this, let's try to run the kung magko-converge. So you just pull this up, and then somewhere in the bottom, meron kayo ditong run button. So just click the run button and hopefully magko-converge siya. So pag nag-green converge siya, ibig sabihin na-solve niyo na yung distillation simulation. So just try to minimize this, and then as you can see, ito na yung simulation. And then as you can see, yung drawing niya, it's much better, It's much better. Meron tayong condenser at may reboiler. Mas mukha talaga siyang distillation column. So ang output nito basically is yung composition ng product. So para makuha niyo yung composition ng product, kung pasok ba siya sa just go to worksheet and then go to composition. And then ito yung ethylene, almost pure ethylene. Ito 99.91. So we can check I'm going to check the tutorial. Ganito rin lang. Lang 99.97 lang. Sandali lang. Parang iba ata yung Kaya 9 times 10 to the minus 4. Parehas naman. And probably konti lang naman yung diferensya, Probably it's just the version of the Sa tutorial is 99.97. Probably I use a different pressure. You can check that out. Pero logical naman yung naging resulta ng simulation natin. Let me check kung saan ako nagkaiba sa tutorial. Dito parehas lang. Sa mga pressures, parehas lang. 300, 350. Yung atang 99.4 ay mass fraction. Yung pala mass fraction. So, mass fraction yung 9 times 10 to the minus 4. So, I'm just going to change that. Ano? So, palitan ko yung specs. I go to design. Specs. Itong comp fraction. So, I'm going to change this to mass fraction. Okay? So, after that, I'm going to return, kita nyo nag-red, ano? So, run nyo lang ulit. Nawala. Ito. So, pasok nyo ulit. 9 E minus 4. Nung nagpalit ako ng mass fraction, nawala yung ano, yung 9 times 10 to the minus 4. Pasok nyo lang ulit. Ayun, converse na ulit siya, ano? Run nyo lang ulit para sigurado. Converse na ulit siya. And then you can check the worksheet. Tingnan natin kung parehas. Ayun, parehas na. No? So, parehas siya. 99.97 yung product natin. Okay, so that's how easy to perform rigorous distillation. Ano bang takeaway dito? Ang takeaway dito, kailangan naiintindihan niyo yung shortcut method on how to perform the shortcut method. On why are you performing the shortcut method. Kailangan yung kunin yung reflux ratio at saka yung number of stages. Gagamitin niyo yun sa rigorous distillation. Tapos kailangan alam niyo yung purpose nung distillation. Kasi by knowing the purpose of the distillation, halimbawa pagtanggal siya ng methane, yun yung magiging lighting nyo. Yung heavy key usually kahit ano lang naman yun. So several components ng i-distill mo. Tapos pagdating naman sa rigorous, kailangan ng dalawang specs, no? So generally ang ginagamit na specs yung reflux ratio na nakuha niyo sa shortcut at saka yung composition ng product niyo. Kung ano yung lower limit ng composition ng product niyo yung gamitin ng specs. Generally ganun. Ano? So ang iba pang ginawa dito is by clicking performance sa tutorial, ano? So by clicking performance, you can plot, no? Plot the temperature. Yun. So just click the temperature and then view graph. So ito yung nasa tutorial. And also the tutorial also plot the composition. So click composition and then view graph. So ganun lang. Okay? Okay, so I hope you can do this, the rigorous and the shortcut distillation on your own, and on your plant design. So to the next video, midterm na to, midterm na tong ating distillation. Okay. So wait for the next video.